right. Let's just make a start then, I guess. All right. Well, yeah. Go ahead. I'm sorry. I'm used to hosting these things.
We have Tim Oxley from NodeUp and other Node projects. He's on here on Read the Source today. He's going to be going through a few things, so I'll let him talk to that. On the panel, we have Cornel Stefanovic. Did I pronounce your name right? I feel awful. I've known you for years.
Not really, but it's okay. Hello, everybody.
And I'm Eric Isaacson. And Tim, take it away.
So yeah, hi. I'm Tim Oxley. I have been working with Node for a number of years, since the 04 to 06 transition, and I'm currently working with NodeSource. And NodeSource does like enterprise Node stuff. We actually just launched a product this week, but I won't advertise. Check us out on nodesource.com. But I've been invited here to talk about Node core streams. So these are something which I feel very fond of, and I use them every day in my work. So I thought it would be good to share some stuff about them and read the source. So let's see, yeah, that was good. So
I love it. I love it.
Let me do some sharing of my screen. What I thought I'd do was, rather than just talk about the streams implementation, I'd have just a sort of a discussion about just like what streams are and why we're interested in using them. What do they compare to? I guess what even is a stream? So the key thing, I guess the key takeaway is that there's two ways of operating on data in a program. One is using buffering, which means you're going to take, let's say you're requesting some results from a database or something like that. All of those results will come across into your process, whatever that happens to be, whether it's Node or Ruby or Java, doesn't matter. You get all of the results in one go, and then you perform some operation on those results, and then you send them down the wire to whoever's going to consume them, whether that's another service or a web browser or whatever. And the alternative to this is to use streaming methods. The difference is basically, rather than pulling all of the data across in one go, you just pull across the smallest amount possible to do some sort of useful amount of work, and then you operate on that, and then you keep the flow of data going from the input through whatever you're doing to the output. So let's do that. I've got a quick example here of what a buffering solution might look like in Node. So this is a fair. I'm just warn people. I've done all of these examples using Node 4.1, which just came out recently, and it supports lots of nice new syntax, such as the arrow and the old backtick, like the template literals, and a few other things. So if this is not transpiled code, it originally was, but then when 4.1 came out, I was like, oh, I don't even need to transpile anymore, so that's really nice. So if some of this stuff throws you off, just a quick primer, like the arrow just translates to a function. So if you could just move the arrow over here and replace it with the word function, and these backticks just mean this is like this is a string, and this is a variable that I'm injecting in there. So anyway, this is a little program. It'll read whatever you pass in as an argument, as a file, loads everything into memory, performs some operation on it here, and I've just picked sort of an arbitrary operation to perform. So I'm just uppercasing the string, and then I'm writing the file out to another location. I'm writing the transformed result to another file. So I've got a little demo here where we can see that this works. I've got some lorem ipsum, just dummy text, and I'm going to run. It's this program exactly as is, running over that lorem ipsum. So what we should end up with is a file called transformed data, which contains our uppercase text. So I run this, and we can then cat the transformed data, and we can see that yes, our program works successfully. It's uppercase. That's great. There's nothing really surprising there, but the data that we're looking at here is type 0. It's only like 4 kilobytes in size. In fact, it's probably smaller than that. And that's probably just the minimum block size. So, this is not a particularly. It's not very taxing, I guess. So, what if instead of reading, a small file, we're reading a large file? So, I've prepared some pretty much the same thing. It's it's lorem ipsum, but it's 300 megabytes of lorem ipsum. So if we run that on, I run this program on that, oh no, we have an error. And in fact, this is actually a bug in the current version of Node. I've opened an issue for it. We've tried to load go back to here. We've tried to load the file in as this data thing. We're loading it all at once, but in the process of switching the data from being a buffer into a string, where there's a maximum string size, string length in V8 or Node, and it crashes. And not only does it crash, it crashes asynchronously. So you can't even catch the error without an unhandled exception error. Like a handler. So anyway, so we can't. That's fine. I mean, the problem that we encountered here, even if that bug was fixed and we did get the result back in the error parameter for the callback, this will actually never work, even with the bug fix, because the underlying problem is that the data is just too big for a string. So let's see what happens if we use a slightly smaller file. So, okay, that's nice. What happened there? So I've got one here which is 100 megabytes, and it should have worked. I'll just I don't want to use the tail. N3 transform data 100. Oh, I don't know what happened there. Whatever. So it's managed to transform 100 megabytes of text. So obviously that's smaller than the 100 megabytes of UTF-8 text string data is smaller than the largest size that you can fit into Node. This sucks that you're limited to 300 megabytes. So maybe there's a better way, and sure enough, there is a better way. Let's compare. We're doing the exact same thing, but using a streaming program. So what we're doing here with maybe start down here. So instead of doing fs.read file, we're doing fs.createReadStream, and that generates a stream object for us. And instead of having a callback, which fires once we've loaded all of the data into memory, we're piping into this uppercaser thing. And in this case, the uppercaser is also a stream. It's a transform stream, which I'll explain later. But the idea is that every time we get a chunk of data, we perform the exact same operation here. So we're just uppercasing it, and then we're pushing it, and then we're saying, "Hey, we're done with this chunk." And then the result of that goes into this other stream, which is a write stream. It's pretty much the equivalent of the previous program. So if we run this, I'm not even going to run that one because that's the old one. Oh, actually, these are all old ones, but I'll make it work. So we do node read file streaming. and then we pass in data 100, 100. It'll work, so it worked. If we do the 300, so remember this one didn't even work at all using the buffering method. It takes a moment, but if we tail the 300 megabyte file result, we can see that it worked. So that's nice. So I mean, just by switching from buffering to streaming, we're able to get around the limitation of the maximum string size in Node. But the more interesting thing here is that we've got is the memory usage of these two solutions. So if we compare these two, we'll see some interesting stuff. So I'm going to use instruments. So instruments is it's kind of like a dtrace front end for OS X. I'm not sure. There's probably equivalent stuff for Linux. Wouldn't have a clue what's available for Node.
Ooh, new stuff.
Ooh. And so what I've got, I've lined up my buffering program with the correct argument. So you set basically when you can choose with instruments, you can choose either a running process or you can have it spawn a process. So I'm having it spawn up my the programs that I just wrote. So I'm going to choose this one. I'm going to hit record, and it runs the program and it generates some pretty graphs for us. So the program's finished, and we can see here that that might be a little small, but the number that's coming up on the screen that's 100 megabytes, and then this is 200 megabytes. So we're literally using 200 megabytes of data to process this. The program that we ran it against the 100 megabyte data set. So so we're using 200 megabytes of data just to do this simple operation.
Yeah, I never would have thought to use instruments for web programs too. That's really interesting. I'm glad that you shared that.
Yeah, instruments comes with like a whole bunch of it's not just for monitoring memory. You can monitor disk usage, you can CPU usage, all sorts of things. And I've used this to great success in the past to debug stuff like deep in Node, trying to figure out why where the memory leak is coming from, and this allows you to let's like details here, a detail view which shows you where the memory has gone. So you and also like what's happening. So you can actually see here it's done all these mallocs, and it's got a thingy call tree. So yeah, and then you can dig into the call tree. It's a little bit like Chrome DevTools, or any developer tools in any browser. So it shows you where stuff is and how much memory it's using. So that's pretty neat. Yeah. So this is this program. Let's adjust it and run it against the streams one. So just need to pass in the new streaming. New file name, and let's run it. Oh, actually, hang on. Sorry, I had the wrong thing selected. Oh. Sorry. Let's try this again. No, that's not right. Delete run to. Okay. Oh. Well, that was right. Sorry. That's not even correct. Streaming. I need to just scroll the screen. Okay. Let's try that again.
Got to roll with the punches in the whole live streaming live coding.
So this bottom one is our previous program. So we can see here again 200, 100. Now this is the new run of our program. We can see here that it's only using 3 megabytes, and it's processing the exact same file and doing the exact same operation. And that's, I think, that's a remarkable decrease in the amount of memory that we're using. And if
that's crazy. How does that work underneath? Like what's happening with the streams?
Well, the key difference between like streams and buffers is that the buffering mechanism needs to pull all of the data into memory first, and then it does operations on it. In this case, the only thing that we need in memory is a small chunk of data that we've read off disk. We read it off disk, then we convert it into, push it into JavaScript, perform our operation, and then write it back to disk. And so at any one time, we don't need the entire data set in memory. So I mean, you can imagine that this makes an incredible difference when it's within the context of a web server. So if, for example, I mean, manipulating 100 megabytes of data isn't like so far-fetched, and maybe it's unlikely that you'd be uppercasing it. You might be performing some other operation altogether. One of the things that I'm describing here aren't limited to reading stuff off the disk and doing string manipulations. This is stuff which will apply to any time that you're reading data from some source and transforming it and then writing it to some other source. So yeah, if this was if an operation like this was inside our web server, if you imagine having a server that has 1 gigabyte of RAM, it would only take 5 concurrent requests before the entire memory of the machine would be exhausted. So that doesn't seem like a very scalable solution, and it's also you're definitely not going to survive being slashdotted or hack and used if you can only support 5 concurrent users. Especially when there's an alternative such as this with using streams, where you can drastically reduce the amount of memory that you use. Even if we increase the size of the data that we're manipulating, so if I switch that up to 300 and run it,
and
we can
see. According to the graph, the application ran faster, right? The stream
in this
application.
In this case, yes, it did. Yeah, it looks like it completed in around 0.01 seconds, and and this one is slower for sure. But yeah, look at this one. This is when we're going over 300 megabytes of data, and still the memory usage is less than 10 megabytes. I mean, that's like that's negligible. I mean, all this data is probably even under. It could probably be even lower if the thing was under more strain. So because the VM will use more or less memory depending on how much strain it's under at the time. So then just one final example with this thing. If I've got one here where I've got like 800 megabytes of data, the same thing, and we can see that the memory usage is, although it does take quite a bit of time, still we have rather than having a linear relationship between the amount of data that you're processing and the memory usage, you have it's just flat. It's a static. What's the word? No. Anyway, it uses just a fixed amount of memory, and it doesn't matter how much data you throw at it. It's still using less than 10 megabytes of heap, which is really cool, I think.
And is it possible to limit this amount of memory usage?
Yes. So, which brings me to my next point: memory usage versus throughput. Now, that's actually that's the trade-off that we're making here. Although in the 100 megabyte case, we did actually manage to get we processed it faster. How do I put it? So yeah, what we're trading here is again, if this was inside a web server, because we've got a stream, we can start sending the response to the client before we've actually completed the full operation. So while with the buffering solution, we have to dig all of this up, do the operation, and then only after you've completed it can you even start to send anything to the client. Yeah, with the streaming solution, you're able to start pushing stuff the moment you've done some amount of useful work. You can start sending that useful work to the client, which also means that the client doesn't have to keep the whole thing in memory as well. If the client has a streaming system on the other end, and yeah, so we're trading memory usage for throughput. And the interesting thing that we can do is there's a flag in this one here. There's a flag that we can use in when we create new streams. It's called high watermark, and this allows you to control how much data that you will operate on in one go. So the default is 16 kilobytes, so it's a value in bytes. And you asked earlier, how does this work? So the concept is you're taking a large task and breaking it up into lots of small ones. So when I run this program, the first thing, I've got a pass-through stream here, and pass-through streams are typically used for sort of side effects that don't affect the flow of the data. So all I'm doing is logging the length of the chunk that I get. So if this was the buffered solution, you get one single chunk, and that chunk length is the entire length of the input data. But with the stream, we can see. Yeah, go ahead.
Sorry, Tim. Could you zoom in a little bit on the text so that we can see the code a little better? Thanks.
Yeah, how's that? Better?
Yeah, I think it's better.
I'll get rid of this. So this is the same program that we had before. It's just got this pass-through stream, and I'm going to start playing around with this high watermark. So if we run this, what is it called? Read file streaming. High watermark. And we pass in, let's say, the 100 megabyte file. We can see here it outputs an awful lot of 16384s, and that's 16 kilobytes. So it gets a whole bunch of 16 kilobyte chunks, and then the final one doesn't quite meet the 16 kilobyte boundary, so it's smaller. So what we've done is taken that 100 megabytes and broken it up into lots of little 16 kilobyte chunks, which makes it a lot easier for the program to to process, because it doesn't need to load at any one time more than 16 kilobytes or so of data into memory. And like I was saying before, we've got this high watermark control, which allows us to adjust how big the chunk size is. So if I switch this down to just 1 kilobyte, we can see that it outputs a lot of 1024s. And in fact, it broke that thing up into so many chunks that I didn't have the patience to let it complete. So if we, remember this was 16 before, let's just switch it to 8. Actually, take it back to 16. So now I'm going to pipe this into WC, counts the lines. So it's broken that 100 megabyte file into 6,403 little chunks, approximately. If we decrease this number, so the high water mark, so it's saying that we're not going to buffer more than 8 kilobytes at a time. We see that it's broken it up into 12,000 chunks instead of 6,000. And the more we lower that, the more chunks we get, the higher we raise it, the less chunks we get. Now, where this is interesting is when you see the memory usage. So if we go to streaming high watermark, and so at the moment it's set to what's it, 16. Let me run it. So we can see here that when it actually uses up to 20 megabytes of memory, but it's actually even a little bit slower, and that's probably due to this console log. If we pull that console log out, one more time. Console log is something which you need to be aware of in your program so it goes much smaller. It's a horrible. We often use it for debugging to try to figure out why something is going wrong, and so often the solution might seem to be add more console logs, but console logs dramatically slow your program down because it's due to the streaming nature of streaming the text to your terminal. So this is actually the same program. One's using this is the console log version, and this is the no console log. So this is much smaller. And also, we'll note that if we go back to our original, this is the streaming one. It's a little bit bigger than the. This is actually faster because we're buffering more data. So this is what I was trying to get at with your trading throughput for memory usage. So if you increase the high watermark for your stream, it means that you're able to process the same amount of data using less chunks, which means that you can potentially increase your throughput at the cost of increasing the memory usage in your program. So that's a useful setting to be aware of that you can play with. Yeah.
So with fs.create read stream, right?
Yeah.
Is that in underscore read stream in the streams, or is that like its own file? So what does it do that makes it take so much less memory? Like, can we go through some of the code in Node there?
Yeah, we can.
I mean, we don't have to do it.
Okay, I've got a couple of little ranty things that I wanted to just babble about, but that's pretty much the next thing that we cover is how the stream works. So one of the other things which I see happening in the Node ecosystem is that we get things which are streams but are not streams. So we'll see things like things which emit data events. They're an event emitter. They'll emit data, but they're not a stream. And this is there's a couple of CSV parsers which are actually quite popular, which do this, and it's a headache because it means that you don't get the different APIs have different events. So, for example, one of them might emit a completed event as opposed to a closed or an end event. You often don't get pipe. You often don't get back pressure, and you don't get any kind of buffering control. So the solution is to just extend the stream readable class. So this is the same code that I had before, but you just extend readable, and instead of emitting data events, you just push, and that pushes into the internal buffer. So yeah. Now brings us to part 2, which is streams in Node. So,
that's a really good point too with APIs in general. Like on the front end, even they're just so varied, and people just they don't think that maybe this would be easier if we had more standardization behind this.
Yeah, one of the ones which I find a little bit annoying is Socket.io actually. So Socket.io has the concept of a message. So instead of emitting data events, they emit message events. And I don't know. It would have been nice if that was, instead of being this sort of custom API, custom Socket.io API, it was just a stream API, because the stream API is something which there's like so many things which work with streams, and then by building your own API, you're kind of cutting yourself off from that.
It was one of the pioneers, though, for that. So I think it's probably a lot of legacy code they have to go through to
absolutely
do all this. So, but
That's
definitely.
True, yes. So you'll find all of the stream implementation stuff in Node is inside the lib folder, and in fact, all of the JS stuff is inside the lib folder. A lot of people never open this folder up, but I highly recommend it because it's actually there's an awful lot of good quality code in here, and which is very well documented, and which made my job quite easy when it came to trying to understand what these things do. So, but this is not what we're actually going to look at. We're going to look at a thing called Readable stream. And the reason why we're going to look at that is because it is the Node implementation of core streams. This is where the development gets done. And so what happened is when streams was moving from streams 1 to streams 2, Isaac used this repo, well, under his name, to, prototype the new streams implementation. And then that, once it was good to go, then it got copied into Node. And then what's been happening is that this has been the location that more the ongoing streams work has been happening, and then it's been pulled into the Node repo as it matures, I guess. And the other reason why I'm going to talk about this is because Readable, if you depend on the core streams, when you update Node, you're at the mercy of whatever streams implementation comes with Node. But if you depend on Readable stream, you're able to version which version of streams that you're including in your application. So if, for example, some bug gets fixed in streams, but that breaks your application, and it has happened, you're immune to that because you're able to control when you update the streams implementation that you're using. And the same goes for libraries as well. It doesn't have to be just apps. So rather than require stream, you should require Readable stream. And it's not just the Readable stream implementation, it's all of them. It's a bit of a misnomer. So if we go into the lib folder in Readable stream, we can see all the stream implementations. So that's pretty much what I just said. But first, let's talk about the stream implementation that's in Node. So there's two parts of this. There's stuff which is implemented in Readable stream, which is readable, writable, transform, etc. All these are like buffering streams, and they implement things like buffering. That's the key thing. While in Node, there's a in Node there's a stream. We just want the stream one. There's just this base streams implementation, and I think that. So I'm going to talk about this first because I feel like this implementation gives you, I guess, a taste for what's happening in the Readable streams, like in the buffered streams, without all of the additional complexity. Because the streams, the Readable stream, they're kind of they're not the easiest. So the basic idea with this stream is that we've got an event emitter which emits data events. So if you require stream, just require stream, you get this thing, and this is probably the closest thing to the original implementation of of streams back in the days of Node 04, etc. So the interesting parts of this are so the basic idea is when you're reading something. So for example, if you're reading it from the disk with a stream, you're getting, instead of getting a callback at the end once you've got all the bits, it emits these data events which you can listen to. um, my styling is a bit funny, but the built-in require stream, like the simple one, it implements a really naive pipe method, which gives us sort of a back pressure mechanism. And the basic idea is that if we can't currently write to the destination, we're going to pause ourselves. So if we look here, so pipe is the way that you compose streams together. So before in the example application that we had, we created a read stream, then we piped it through our transformation, which uppercased it, then we piped it into a writable stream, which was a new file. So pipe is sort of like the key composition mechanism for streams. That's why I'm covering it here. So in this implementation, basically, whenever if I pipe A to B, then whenever A gets data, we fire this onData event, and then basically if B is writable and we can write to it, and we can't write to it, then we pause ourselves. And what pausing means is that it means that we're not going to continue like reading from whatever our data source is. So, for example, we're not going to keep reading things from off the disk because we've got nowhere for that data to go. Does that make sense?
Yeah, can we zoom in on that a little bit too? 'Cause it's hard to read the code.
Oh, yeah.
I'm old, so.
Oh, no, that's fine. How's that?
Much better, thanks.
Okay. So, yeah, so whenever we get a data event, we fire this, check if the thing, if it implements the writable interface, try to write to it. If we can't write to it, then we pause ourselves. And so the second part of that is this draining. So once we're paused, we need a way to unpause ourselves, and that's this one. So we resume when the destination says that it fires this drain event. And what the drain event means is that you're writing to something and it's blocked. You can't write to it because of whatever reason. It's probably like its buffer's full. A good example might be like, for example, the disk that you're writing to, it has a maximum amount of bytes that you can write to it. Or if you're writing over a network, there's quite a low amount of data that you can write over the network. So you're probably going to hit a point where the destination buffer fills up and you can't write anymore because, well, the buffer's full. So once the buffer's full, that's when this thing will come back as false, which means we're going to pause. And then the way that the destination signals, hey, it's okay to write to me again, is it signals that its buffer's been drained. So there's no more. I'm not blocked anymore. So resume. So that I think makes the concept of what we're describing here is back pressure. So meaning that if the thing that you're writing to is full, then you stop, and then because you've stopped, because we're paused, anything that's writing to us. So, for example, if we're if we're not a readable, we're a readable and a writable, like a transform stream or something, then we're going to communicate that, hey, you can't write anymore back to whatever's pushing into us, all the way up to wherever the data source is. So this is back pressure, and it's a very powerful mechanism, and you need to implement it whenever you're doing things where it's possible that the pipe gets full, and it's always possible. So this is one of the main reasons why you want to use something like streams as opposed to just your own custom stream-like implementation. So the other interesting thing here is auto end. So when you're reading from a stream, if you're when you're out of data, you get an end event basically, and that fires the. So the idea is that when you are finished, then you want the things which are downstream from you to also finish. So that's what is implemented here. But what you can do is it's got an auto-ending system. So when you build the stream, you can put in your own implementation if you want, which means that you can control when the end event happens. So that's another, I guess, interesting thing here. You're everybody following that?
Yeah, my brain is racing. I'm trying to figure out like streams when you're going to do all these things with streams. Like I know there's a Streams API being built for front end for the browsers. So
Correct.
like all these things like offline and network connectivity are running through my head. Is there any of that? Obviously not browser issues, but is there any of that network connectivity an issue with these?
Well, I guess one thing, if the the default thing that happens if the connection goes down is so if the stream that you're writing to is a TCP stream, or HTTP stream, if that stream dies, then your data dies as well. But you can implement sort of like a wrapper around that. So a good example is Dominic Tar Reconnect. So what Reconnect allows you to do is you wrap up any stream, it doesn't matter what it is, and it will reconnect if the underlying stream for some reason dies. So, and you can implement your own custom logic. This will work for WebSockets or anything. So if you implement something like this, what can happen is so basically you just want something which isn't going to shut the whole thing down when one of the streams has a problem. So that's what Reconnect will do. It sort of acts as a bit of a buffer, I guess. Now, when data is being written into this, Reconnect itself will have its own buffer. It's a stream. So when so data will be written into Reconnect's buffer, and when the connection comes back online, all the data can start flowing again. In the meantime, it'll pause itself and then also pause all of the upstream streams, and also have some data buffered as well. So yes, network connectivity and fault tolerance is something which is almost trivial to implement with streams. So that's a nice thing.
Tim, I have a question.
Sure.
If one of the stream dies, are we going to get, is the end event going to be triggered, or are we going to have only an error event triggered?
So, yes, if one of the streams dies with an error, then basically everything goes down. And I'm going to cover that in just 1 second. So I'll get to that.
Always ahead of the curve, Cornell.
Yeah. So with this stream implementation, this just require stream, you shouldn't actually use it. It's not. It's mainly around for backwards compatibility with older systems which required stream, as opposed to stream.readable, writable, transform, etc. And yeah, it's limited in usefulness because it's a push stream, which means that it doesn't matter whether anything's listening, it'll still fire events, and it doesn't support buffering. So yeah, don't actually use this. Ideally, the code. This code actually doesn't even get run, even though it's in Node. All of the other stream implementations completely override everything that this class does. They all extend from it, but they just override. Well, the only thing that it does is this pipe, basically. So they all have their own pipe. So this thing just basically does nothing. Now, stream error handling. So back to your question. With streams, it's YOLO by default. So any error events that aren't handled are thrown, and we can see this in the stream implementation here on line 70 to 76. If we get an error, so if the source gets an error or the destination has an error, basically we remove all the event listeners, and then we do this. This is the trick. If there is nothing listening on the error event on the source, we just throw. And if this happens inside something which is asynchronous, you can't even catch that. There's nothing you can do. So it's not like all of the streams suddenly have an error and that error is propagated or anything. It's literally just a throw. And in asynchronous JavaScript, throwers basically crash. And the only way you can capture this is with an unhandled uncaught exception handler. So process on uncaught exception is the only way that you can actually do anything with a stream error. So if we go back to this, so often you're taught to use streams, like to say you start at a source and then you pipe through all these things, but this is like completely it's not very robust, because if any of these streams emits an error event, your entire process crashes. So that sucks. So the only way to really get around it, the only way to get around it without using third-party tools is to do this awful thing, where it completely ruins like the nice chaining API that you get with pipe. Yeah. Anybody got any questions?
Very gross. Can you just keep the stuff zoomed in so it's easier to see though, please?
Stuff. Oh, sorry.
Oh, yeah, this is good. But like when you're on the GitHub pages or anything like that.
Yeah. Sorry. Okay. All right.
No, it's all good. It's interesting stuff. This is great.
So yeah, I think the way that this works, where the errors don't kind of bubble up, it's kind of crap, because most people just don't do that. Most people just do this because this other thing's like really ugly and it's awful.
Because we never have errors in our code, so.
Yeah, exactly. So and the other like stream errors are often things which are like they often occur only in production. They're like there'll be things like a resource you can't write to a resource or something horrible like that. And so these are exactly the type of errors that you want to be catching. Anyway, there is a solution. There's two tools. They both use the same system. I'll just show Pumpify. Pumpify is the tool that Mississippi uses under the hood to do this. But with Pumpify, you can create a pipeline of streams. So, for example, here, zlib create gunzip tar extract. And if anything inside the Pumpify pipeline has an error, all of the streams will be closed and destroyed. So and you get a single error at the end. So that's like a really nice feature. And I feel like if you're going to be using streams and you're going to be piping them all together, and you don't want to be attaching these error events, and you want to be robust, you have to use something like this. The reason I brought up Mississippi is because Mississippi is a bunch of it's kind of like a toolkit for using streams, and one of the tools is pipe, which allows you to pipe a whole bunch of streams together and then attaches the error handler, just like in Pumpify, or uses Pumpify. So yeah, that would be my recommendation for making sure that your streams are robust. Did that answer your question?
Yes.
Awesome. So now onto the real stream. So we've just been talking about the node stream, and all these other streams are the ones that are far more complicated, and they have they do buffering. So before I was complaining about buffering, because that's what increased the memory usage of our program. But if we don't do buffering, so the example would be to actually change this high watermark back in our program to 1. So as in that will do 0 buffering. We're going to process a 100 megabytes doing no buffering, so just the chunks as they come off the disk. If we run that, well, I can tell you what happens now. It basically it doesn't complete in any kind of tolerable amount of time. So you have to do some amount of buffering in order to get decent performance out of your application. But you don't want to do too much buffering, because if you do too much buffering, then you delay the response and you also increase the memory usage. So all these tools implement 16 kilobyte buffers by default, basically the idea is memory versus throughput. Additionally, the other stream tool, it didn't really matter what data you were pushing through it. It just handles anything. But all of these ones, all the Readable, Writable, etc., work specifically with buffers and strings, because they're designed specifically for reading stuff off the disk and doing I/O related stuff. And I/O related stuff, you want to kind of do the least amount of work possible, because typically I/O is that's the biggest bottleneck, and it happens a lot. So you don't want to be doing lots of work when inside your whenever you get I/O happening. So buffers are something which most people don't touch unless you're dealing with I/O, and so I remember them. They were quite a mystery to me, and I didn't really understand what the hell they were. So buffers. What I'm talking about here is the buffer class inside Node. This is not something which exists in the browser. This is something which is specifically Node, and buffer allows you to create just a big slab of memory, basically. It's basically malloc. So if you're familiar with C or C++, when you allocate, if you want to allocate some arbitrary amount of memory, you need to use malloc. And buffers are how we do that in Node. They're an untyped chunk of data, so it just, if you're reading something off the disk, it doesn't do any transformation to it. It's literally just the bytes as they are on the disk. And the reason why we needed buffers originally was because there was no ability to handle JavaScript has no binary data capabilities, and if you're a lot of applications want to be manipulating binary data as opposed to string data. Now, thankfully, due to the needs of things like the web audio and WebGL APIs, the browsers implemented typed arrays. So typed arrays are pretty much exactly the same concept as a buffer, and they're built straight into JavaScript. So if you get like a uint8 array, and it's the same thing. You basically get a big, well, they're not untyped. They're typed to some stride size. So like in this case, it's a uint8 size, and you've got uint 16, 32, etc. But the point is that these are just like just big chunks of memory, and you can access the individual bits in there because you don't want to be converting to strings and back to buffers and then back to strings. That's bad.
Are you typing? Are you typing some code? Because we're seeing your presentation right now.
Oh no, that's right.
Okay. Okay. Cool.
Yeah. Well, hang on. So can you see this? Is that like oh, that's bad. It's because I went full screen, and I guess the screen capture doesn't capture the full screen. Okay. Can you see code now?
No, actually, you're sharing only the browser.
No, I didn't say that. I didn't tell it to do that.
I don't know.
Hang on. Let's. Oh dear, that makes some of the stuff probably a little bit awkward. Hang on.
It's interesting though, looking at the different streams in Node. I find it very confusing.
We lost Tim.
He'll be back. It's been a few months since we did one of these, so it's bound to happen.
Yeah. Luckily, we got a good presenter for this one, so
yeah, some interesting stuff on there for sure.
There he is.
Okay, I don't know what happened.
Welcome back.
Shall I continue, or have you got any questions while we're...
Carry on. This is good stuff. I was saying that the Node streams, they were always very confusing to me, and I'm really glad that on GitHub I found, I think it was Substack, who had a like the core streams wiki thing where you could read.
Called Stream Handbook.
Yes, the Stream Handbook. That was really good history on streams, so it kind of prepped me to kind of look at this stuff, and the pass-through was always very confusing to me, like why that, but you cleared that up for me actually, so that's awesome.
Oh, awesome! That's great. Yeah, I think that my understanding of streams was like specifically this thing was where I learnt most of the stuff. I guess that Stream Handbook is awesome. I recommend everybody go have a look through it, read it, and try the code examples as well. So, yeah.
Yeah, we'll put your presentation if it's up, on there too. The links for that and that if it's available, and the and that particular handbook as well in the notes.
Yeah, I can do that.
So can we go back and take a look at more of the code pieces of it and how that's working?
Yeah, sure. So let's go. Let's just go back to the code.
Yeah. I know we're running up against time, but it's really interesting stuff. I'd like to take a look at it.
Yeah, for sure.
A few minutes, whatever.
Yeah. So readable stream. Readable stream is it's the concept of where it's a source. It's where data comes from. So if you've got, for example, you'll know when we did that fs.create read stream, well, that creates one of these things. And that's in contrast to a writable stream, which is like it's a sink. It's where data goes to. So readable.
We're not seeing what you're seeing on your screen though right now.
Oh my god! You're just looking at my face. That's embarrassing.
Yes. I'm like, it's not on his head. Where's the code?
Okay. All right. How are we going now? You can see yourself? Okay. I assume yes. Okay. Back to here. So.
Also, please zoom in a little bit.
Yes. Probably go about there. How's
Perfect.
Awesome.
So the stream is broken into two chunks, I guess. One is the readable stream. One is the readable stream API, which is all attached to the readable prototype. So we'll see here, like push and unshift is paused, etc. But then it also maintains a whole bunch of its own state, and that is created through this. That's maintained through this object called readable state. So readable state. Well, one thing which it tracks is whether when you create a stream, you can put it into a thing called object mode. Object mode means that rather than dealing with the buffers, which I was talking about before, it can deal with just any arbitrary JavaScript object except for null. Null signals that the stream has ended. So if we look at how this works, so the readable state just, I guess, collects the properties when it's first created. So this is where, for example, it sets up the high watermark, which is the 16 kilobytes thing. It will also cast it to an int, does a bunch of stuff. It sets up all of this, this state, and then it becomes this underscore readable state object on your readable instance. Now, so the key thing that you want to be doing probably when you create a readable stream, you are going to be pushing data into it. That's how so you, instead of like emitting data events like you did in the previous one, you push it into the streams, or use this push thing with the concept. The concept is that you're pushing it into the buffer, and then the readable stream decides whether it's going to emit data events or not, whether it's going to hold on to it and wait for the buffer to fill up. So what we do here is, first, we're checking whether we're in object mode or not, and if we're currently not in object mode and we're trying to push a chunk. Streams can they support multiple different encoding types. So the default encoding is UTF-8. Well, it's a buffer actually. But if you supply an encoding, I'm pretty sure the default is like UTF-8 or something. But you can supply like set encoding, all these other readable encoding, things like hex or whatever. So whatever the data type that you're working with, sorry, where are we? Back here. Whatever the data type that you're working with, you can set an encoding appropriate to that data type, which is nice. And then we call this thing called readable add chunk. Readable add chunk will first make sure that that the chunk is it's a valid chunk, and what a valid chunk is basically if we're not currently in object mode, the chunk needs to be a buffer, a string, or null or undefined. Otherwise, you'll get an error, which is this can if you come across an invalid non-string buffer chunk error, and you will, I bump into them all the time, it's probably that you forgot to set your stream into object mode when you were initializing it.
Why so many if conditions in that one method?
It's got a whole bunch of. It's quite a complicated state machine. There's a Chris Dickinson's stream state.
Yeah, I would imagine there's a reason, but I'm looking at it going, whoa.
Yeah, it's
a lot.
There's a lot of. No, it's not this one. Hold on. I meant to grab this before I started, but I forgot. Dickinson. Damn it. There's a flowchart for the state transitions that a stream goes through, and it's very complicated. So I guess that's why there's lots of if conditions, is that there's backwards compatibility with all the things, I guess, but also it needs to support like the buffer type, the string type, object mode, and then there's also the concept of you can push stuff to the front or the back of the stream. Well, not quite. As in, you can be adding new data, or you can be returning data back to the stream if you read too much. So this can happen, like if you're trying to parse some protocol, and let's say, for example, it's an HTTP protocol, and you find the chunk that you've got. Halfway through the chunk, you get the end of, for example, the HTTP headers, and now it's time to finish your parsing. You can use what's it called, unshift, to push the chunks that you just that you read off it back onto the stack, so that it'll go so that, well, you haven't consumed them. So then the next thing is free to consume those chunks. Now, any questions there? Following?
No.
Now this thing is, it looks pretty awful. If there's an error, we admit an error. If we end up, if you hit a null, that means that that's the end of the stream. So then we start like closing the stream up. If we're in object mode, then we are going to have, oh God, all this logic for handling that. I guess the interesting thing with this is we've got this. We've got the state decoder. So this is the thing which, when we set the encoding, when we get to this point, if we've set an encoding and we're not returning something, we do this basically. And then what else? It's pretty chunky stuff going on here. This is where it gets interesting. So the streams can be in one of two modes, and this is a nice thing which has been added now to if you're transitioning from node 0.10 to node 4. Before there were two distinct modes. One was sort of a backwards compatibility mode, which was called non-flowing mode, and then there was flowing mode, and this corresponds to the concepts of streams 1 and streams 2. Flowing mode is where basically it's a pull stream, so no data flows unless there's something to consume it, and non-flowing mode is basically, it's a push stream, so it just emits data as the data happens. The problem is that if you, for example, you need to attach, if you're attaching listeners after the like asynchronously, if you need to attach listeners asynchronously, that becomes a headache, because then you need to, well, you kind of can't. You have to throw stuff into a buffer and then attach listeners to that or something. It becomes a headache. You can't do it easily. So, does that make sense?
Yeah, Tim, I have a question. What happens to the chunks that were not consumed when you pause the stream?
They just sit there in the buffer.
Okay, thank you.
Yeah. So if we're flowing and we have some stuff in our buffer, what we do is we emit this data event, which is the this allows us. So hang on, back to the streams 2, streams 1 problem. In 0.10, if you attach an on-data event to a stream, it'll give you an error. It'll complain. It'll say, hey, you can't do that. Can't switch. Well, if you've used pipe and then you attach an on-data event, it'll complain saying, can't switch to flowing mode now, or non-flowing mode now because you're currently flowing. Can't switch between the two push and pull modes. But now with some changes that have landed in Node 4, you can freely add data handlers wherever you want, or use pipe. They work interchangeably, which is a really nice addition. So if we're flowing and we've got stuff that we emit the data, and then we do this interesting thing, which is the read 0, which signals that we don't want to read anymore, but we want to tell our consumers that that we're readable, as in there's stuff in our buffer to be read. God, it gets a bit complicated here. And then here, if we're not flowing, we add the chunks to our buffer. So basically, if you push into something and we're not currently flowing, the things just go into the buffer. Does that make sense?
Yeah, definitely.
So trick is there. It will also do this maybe read more thing. So maybe read more. So, and this comes back to a question earlier about whether streams are like sync or async. So one of the things that it does here is basically it forces the thing to be async through this process next tick. Otherwise, it'll be all happening in sync mode. So, oh god, this is confusing. Let's think about this. Streams will work whether the underlying data source is emitting stuff synchronously or asynchronously. And streams go through all of this, state stuff to ensure that those things, it's sort of, it's basically transparent. But the idea is that once you're in, once the program is, if the stream can be read synchronously, it will do that. If it can't, it'll do it using asynchronous things and asynchronous calls. And the reason why that's powerful is because it means that, like before, when we were operating on our large buffer with the FS read file, when we were just doing the operation of toString, that can be quite expensive. And as you know, Node is single-threaded, and the whole thing can be it'll lock the whole thing up. Lock your whole process up if it's stuck doing some kind of heavy CPU load. So a neat thing about streams pushing things into asynchronous land is that it allows the stream to break that task up across multiple ticks of the event loop, which means that you yield to the event loop, and it allows Node to do what Node's good at, which is lots of little tasks. Lots of little tasks as opposed to big tasks. So I think that answers the question about whether, like, how streams can help you not block by breaking stuff into lots of little asynchronous tasks.
So with a lot of this, we think I started playing Koa recently, and using the whole paradigm of generators. So would you recommend Flow using streams to generate generators? Well, then you could stop the process and then continue to take the stream. Yeah, I actually haven't played around with that much, to tell you the truth. I'm quite excited about the fact that we're getting asynchronous iterables eventually, and that's basically a stream built into the language. That's basically all a stream is an iterator. For of syntax. I'm not sure what the eventual syntax for a
async iterator is, because at the moment all of our the iterators that we have at the moment are all synchronous, which is a bit of a headache. But yeah, the iterators we have now can be iterated over using for, of, or you can use array from to kind of convert it into an array or whatever. Yeah. What would you like me to do now?
No, that's great. I think it's a lot of information. If you have stuff that you think makes sense to wrap up with things, or if we're good, then.
Well, I mean, for the sake of let's not go too crazy with time. Maybe the key things to note are the Readable is a you have a read event, and you can push data down into a pipe using the Readable. The Writable is you push data into it, and it's got its own buffer, and you can consume stuff from the Writable's buffer into, for example, write it to the disk or whatever. Then you've got a through stream. Then you've got a duplex stream, and a duplex stream is all it is a readable stream and a writable stream in the one place. So if you call .pipe on a duplex stream, it will use the readable stream. If you write to it, it'll use the writable stream. So it just sort of combines the two APIs into one. And then there's the concept of that one's
so much.
There's so much. These aren't easy. So duplex. So you can see here, it just literally has a readable and a writable, and it just merges the two APIs. Simple. And then something which confuses a lot of people is the difference between a duplex stream and a transform stream. A transform stream is also a duplex stream, but all it does is it's kind of like a particular type of duplex stream which allows you to pass in a function which, I guess, maps the stuff that's coming in on the writable end to the readable end. So classic, well, we implemented a transform stream before when we did the uppercasing. So the input was transformed into the output. So that's kind of the difference. Like with a duplex stream, there's no system for like connecting the input to the output. You have to do that yourself. But with a transform stream, it's sort of got this thing called underscore transform, which you can supply, and it allows you to like map or filter over your data. Final one after duplex and transform is pass-through. And pass-through, yep, go for it.
Tim, do we have any custom events for the transformation stream, or?
I've never used any. There's are there? I don't think so. To me, I just treat them the same as readable and writable. The only thing that I ever use really is the overriding the transform or overriding the flush. So quickly flush. Flush allows you to, after your stream is ended, sometimes you might want to write a little bit of additional data to. So, for example, let's say you're writing you're doing streaming JSON or something. When the stream closes, maybe you want to close the JSON with the curly brace or something. That's what you can do. That's the kind of thing you can do with flush. And final one, pass through, which we talked about briefly before. It's basically transform stream that doesn't transform anything. It just allows you to do things like attach logging to your streams, or perhaps inspect it, or do something which is it allows you to apply side effects to your stream that don't affect the stream itself.
All right.
Well,
we're out of time for this one, but Thank you so much for coming on.
No worries.
I know people can find you if you don't listen to it already. For Node, you're one of the hosts for Node Up. It's a podcast.
Yep.
It's fantastic. I've been a listener for a while. D. Shaw is on there all the time, and it's great. You guys do a great job, and I know he hasn't been on as a host for a while, but you've been doing a great job doing that. And I really appreciate your insights on streams and coming on. If people want to help with Node and give back to the community and help on these projects, can you list the files on the notes and maybe
for sure.
how people can find you?
Yep, absolutely. I'll package up that presentation that I've got and make that available so people can look at it.
Okay, and congratulations on the enterprise release from Node.
Yeah, it's pretty exciting. We're for a lot of us, it's like our first. It's the first product that we've been involved. I guess like building as all together. It's like a thing that we are building as opposed to something that somebody else is building. That's it's a really nice feeling.
The community's really come together. It's a good community.
Yeah, excellent community, absolutely. Yeah.
All right, we're gonna sign off. All right, this has been.
Thank you very much for having me. Yeah.
Thank you.
Thank you.